Right. Okay. Uh, right. 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 Okay. Uh, I think last day I think we discussed vector revision fully and we have done some questions, but still we could not do past paper questions related to vectors. We could not do that, right? But that is there. And also now today I am planning to start unit 4 from expansion, especially solid expansion, right? Now it doesn't matter if you didn't learn anything in unit 4 heat. It doesn't matter. You will be able to understand solid expansion today, right? Because I'm going to revise all the theories at first. And with the time availability, we want to check whether we can do past paper questions or not. Let's say in case if we could not do past paper discussion today, definitely we'll arrange a different time slot to discuss heat past paper questions, right? Today plan is solid expansion. Somehow we'll revise everything that we should remember, that we should learn under solid expansion. That is our target. That is our target. That is our target. Right? Now I think it's fine. That's our target. And I think now this is the thing now. I thought of do this 25 revision class bit different than the previous year's revision classes. So now normally what we do in revision class generally is when it comes to English medium, uh, the common practice of doing revision classes means they take 1 day per week and they do questions, right? So while doing questions they revise the theory, right? But I thought that the efficiency, the effectiveness of doing such a revision class is not that much beneficial, because let's say if one student has faced 24 A level exams but that student could not cover all the theory sections, if not the student has missed some theory sections, in that case when revision class is going, like doing questions and revising, sometimes the students are not able to get that idea. So that's why I thought of do my revision class revising all sections, right? First we now, like how we do in theory class, but we can't take that much of time to discuss theory in this revision class, but we basically we discuss all the questions, all the theories, right? We don't skip anything, but we discuss all the theories and we revise in solid expansion. This is what you should remember. This is the equations. This is how this comes. But we don't go deep, right? So when we go for a theory class, when you come for my theory class, you understand every theory. We go in deep and I explain. But in revision class we don't do that. So that's why I thought of I'm doing this revision class only through online, right? So I thought to start like this. So now once in a week, I think every week now plan to keep revision sessions three revision sessions to revise three sections from three different units: unit 2, unit 3, unit 4. If you don't if you didn't refer if you didn't learn unit 2, that doesn't matter, you will be able to understand unit 3 and unit 4, right? So without harming any of you, I thought of do three sessions parallelly per week from three units. Then we are revising them, and then next week sometimes we arrange three sessions to do past paper questions. Likewise, I thought of do a full revision. That is the goal of this. Now I since I started these classes last week, now still I'm planning what to be done, and still I'm preparing some tunes and PDFs. That's why now I ask you to now I just send some what PDF documents, and I ask you to now take printouts. But next month onwards, most probably, whatever we do in that relevant month, I will share a post and I will include. In the first week, we are going to discuss these sections. In second week, we are going to discuss these chapters. And also, in February, before second week, I will deliver all the PDF and all the tunes related to that revision. That is the plan. That is the plan. And also now three revision sessions per week, and also we based on what we learn in the revision class, we write a paper, right? A standard paper. What will happen with the time, the content, the theory that we cover in the revision class will be sufficient to do a full paper. In that case, parallelly we are doing this model paper on Saturdays, and three revision sessions per week, and also past paper discussions, right? And also we will revise all the practicals also. Now I will from February onwards, I think I will give the right idea of this revision class. Still most of you not that much familiar with the revision class. Okay, right. Okay, now we'll start this solid expansion. Okay, now give me 1 minute. Now we'll revise this unit 4. It's a big lesson, right? The largest lesson in your syllabus, unit 2. The second one is unit 3. Then the third largest in your syllabus is unit 4, right? And it's very important lesson. It's completely all right if you didn't learn this unit before, also completely all right. In this revision, we will revise everything without skipping any single point, right? Now, unit 4, heat. Okay, heat. And there are plenty of chapters under heat lesson, but today we are planning to discuss only solid expansion, right? Solid expansion. Now, generally, expansion in unit 4 heat, we will learn expansion under three different categories. Expansion, we discuss solid expansion. Today we are learning only solid expansion, right? Then liquid expansion. Then second one will be liquid expansion. Solid expansion is first one. Second will be liquid expansion. Right. Okay. Right. Expansion, solid expansion. Then we have to learn liquid expansion. The last one will be gas expansion. Right. So now gas expansion, we learn as gas laws. So that is also under need for gas expansion. We learn in gas laws. Gas expansion we learn in gas laws. Right. So now today plan is to discuss solid expansion. Remember, solid expansion we can further divide into three subcategories. One is linear expansion, right? Linear expansion. So then we can consider area expansion. The last one will be volume expansion, right? So the content, when you compare the content of linear area volume expansions, normally we have to give some time to discuss linear expansion, because the applications that we see in our daily life are mostly belong to linear expansion. Now, what is basic expansion? We all know expansion means, right? Now, if you consider length, expansion in length means what? Increase in length. Okay. Then, when you consider an area, expansion in area means increase in area. If it is a volume, expansion means increase in volume. And you know, this expansion phenomena relates with the temperature. Okay. Expansion is related with the temperature. Okay. Now, if I briefly explain the mechanism, how this expansion occurs, I don't take time, I quickly explain. The mechanism is very simple. What happens when just consider a matter. It doesn't matter this is a solid or liquid or gas. Take it as a matter. When you consider this matter, and uh, when the temperature is increased, what would happen? We know that the particles of the matter kinetic energy increases, right? So understand, when temperature increases, kinetic energy of the particles increases. Then what would happen? These particles vibrate with larger vibrations. That means these particles require kind of larger amplitude for their existence. Okay, right? When you increase the temperature more and more and more, the particles require kind of larger amplitude for their vibration. In order to occupy larger amplitude, what would happen? These particles obtain kind of wider space. Now, this is the volume where earlier particles were concentrated. When you increase the temperature, in order to obtain that required amplitude, required vibration, now these particles occupy some kind of additional space. These particles occupy some kind of additional space. That phenomena is we name as what? Expansion. Increase in volume, increase in area, increase in length. That is what we define as expansion, right? So now we are not writing anything for this mechanism. Now I am talking about solid expansion. Especially we are talking about linear expansion. Remember, normally linear expansion belongs to lengths, especially when there is a very tiny stretched, if not there's a rope, if not when you consider a rod of thin rod, right? Linear expansion belongs to the length. Normally, area expansion means increase in area. Normally, just consider plate. When you consider plate, very thin plate, then we talk about the area expansion of the thin plate. And volume expansion is applicable for any object having a volume, right? Area expansion we talk about for thin plate, thin plate, thin plate. So you also write down in that PDF. I think some of you might have taken printouts. Better you write down these points. No, no, we are revising, right? Better you write down all these things what you write. If you think whatever I explain is important, just quickly write down. It's not a theory. I'm not giving a note, but kind of a revision. Whatever you feel important, just write down on that PDF. Now, lean expansion means what? Increase in length. Normally, we consider length as what? Rope, if not rods, wires. Okay. Then now specifically I'm talking about linear expansion, right? Linear expansion. Linear expansion. Now, just consider length. Just take a rod. If you just take a wire, when the temperature is, let's say theta 1, temperature measured in Celsius, if not Kelvins. When the temperature is theta 1, when you measure the length of the wire will be, let's take it as L1, capital L1. Okay. L1 measured in meters. When the temperature is theta 1, the length of the wire is, the length of this object, length of this rod is L1. L1 measured in meters, theta 1 measured in Celsius. Right? Now, what happens when you increase the temperature? When you increase the temperature, the length of this rod, the length of this rope will also increase. Okay. Earlier length was L1. Now this is the length. Now temperature is theta 2. Now temperature theta 2. Right? Now this theta 1 is initial temperature. Now write down these things. Theta 1 initial temperature. Now theta 2 means final temperature. Now what I have done actually from here to here, I increase the temperature by delta theta amount. Temperature is increased by delta theta amount. Then you can tell that just compare theta 1 and theta 2. If temperature is increased, we understand theta 2 is larger than the theta 1. Am I correct? When you increase the temperature, we know theta 2 should be larger than theta 1. That is first point. And what is delta theta? Delta theta means write down change in temperature. Change in temperature. Now in this case, delta theta is increase in temperature. Okay. Commonly we call delta theta as, remember, change in temperature. Write down. In this scenario, as temperature increased, delta theta we name as increase in temperature. Then if I ask you to write delta theta in terms of theta 2 and theta 1, how can you write delta theta? Delta theta means we can write down larger temperature minus small temperature. How you obtain a change? If you want to obtain change in length, final length minus initial length. Change in time means final time minus initial time. Likewise, change in temperature means, remember, larger temperature minus smaller temperature. Then the larger temperature is theta 2, smaller one is theta 1. So therefore, you can write down theta 2 minus theta 1. Some points. Now we noticed when temperature increased by delta theta, the length of this rod increased. Now, what is this length? This length we name as change in length. Delta L means we name as change in length. If not, we can tell it as increase in length. Delta L means change in length. If not, we can say it as increase in length. Okay. Now it's an increase in length. Delta L means change in length. If not, we can call it as increase in length. Now they have found some relation. Now scientists, what have they done? They are doing some experiments and they got to know that this change in length, when temperature increased by delta theta, the length is increased by delta L. Length is increased by delta L. Then they found that this delta L is directly proportional to the initial length of the rod. Okay. This is one proportionality. And also they found this change in length, if not this increase in length, directly proportional to the change in temperature. Change in temperature, right? So what does it mean by delta L directly proportional to length? For an example, just take same rod, just take 2 meter long rod. For an example, okay, I want to show delta L proportional to initial length, right? Think this rod's initial length is 2 meter. This rod is made with, let's say, copper. Rod is made with copper. Take another rod. Take another rod. This rod also made with copper, but this rod's initial length is 3 meters. 3 meters. And what are you going to do? You are going to heat both the rods. 2 meter long copper rod and 3 meter long copper rod under same temperature difference. Now think initially both of them were at 30 degrees Celsius. Both of them were at 30 degrees Celsius. You increase their temperature by 5 degrees Celsius. Then now temperature of 2 meter is 35. Now temperature of 3 meter long rod also 35. Right? So then which rod has larger increase in length? When you do such thing, what will happen? Let's say now increase in length of 2 meter rod is, for an example, 0.1 meter. Okay. Now initially there are two rods of same material, different lengths. Temperature increased by same amount. Then if the increase in length of 2 meter is 0.1 meter, remember the increase in length of 3 meter rod will be, let's say, 0.25 meters. So this proportionality highlights the increase in length, if not change in length, is proportional to the initial length. The rod having larger initial length, obtains larger increase in length. That is the idea. That is the idea of this proportionality. And second proportionality is what? Second proportionality, it says that now this change in length is proportional to change in temperature. What is the meaning of that? Just take two rods having same length. For an example, 2 meter, same material, copper. Now what we do? We increase this rod. The temperature of this rod is increased by, let's say, 5 degrees Celsius. Delta theta is 5 degrees Celsius. But temperature of this rod, the second rod, is increased by 10 degrees Celsius. 10 degrees Celsius. Now, there are two rods of same length, same material, but this rod's temperature increased by 5 degrees Celsius, but this rod's temperature increased by 10 degrees Celsius. Right? So then when you find the increase in length of first rod is, let's say, 0.1 meter. The increase in length of second rod will be 0.3 meters. The conclusion is, when you increase the change in temperature, that increase in length also increases. That is the idea. Okay. Now write these things quickly somewhere else. Write these things. Okay. Then from this proportionality, what have they done actually? They can write down this change in length proportional to initial length into change in temperature. So what have they done? In order to remove this proportionality, they have used a constant. That constant is we call as alpha. This constant is we call as alpha. This is proportional symbol. This is we call as alpha. This length is simple L. This temperature delta theta. So then the first important equation in linear expansion. Now under solid expansion, we can categorize three subcategories: linear, area, volume. Out of these three sections, remember, most important section is linear expansion. The first important equation in linear expansion is, remember, delta L equals L alpha delta theta. right? The first important equation, remember, I erased these things. The first important equation is, right, delta L equals L alpha delta theta. Okay. Delta L equals L alpha delta theta. So the first important equation, delta L means L, right? L means L1, initial length. Initial length is, let's say, delta L means L1 alpha delta theta. This is the first important equation. Okay. So then you should able to define these variables in this equation. What is delta L? Generally, it is change in length. When there's an expansion, we can call it as increase in length. So write down, put an arrow and write down delta L means change in length. In case of expansion, it can be called as increase in length. Then what is L1? L1 means initial length. Alpha, I will tell you. What is this alpha? I will explain. Delta theta means change in temperature. In expansion, delta theta means we can call it as increase in temperature. Increase in temperature. That is one idea. Okay. Now, we identified a constant. I define this constant as linear expansivity. Remember, this is a constant. We call it as linear expansivity. Linear expansivity. If not, we can call it as another word, coefficient of linear expansion. There are two words. One is linear expansivity, other one is coefficient of linear expansion. So now talking about the units of linear expansivity, remember, just substitute alpha. So when you substitute alpha, you can write down alpha as what? Delta L, delta L over. Alpha means we know delta L over L1, if not just L, L1 into delta theta. Now, what is the unit that we use to measure change in length? Change in length measured in meters, right? It's a length or change in length we used to measure in meters. Okay. Then L1 means length also measured in meters. Delta theta means change in temperature. Remember, change in temperature can measure in Celsius. If not, change in temperature can measure in kelvins. Let's say this temperature measured in Celsius. Then remember, what should be the units of? What should be the units of linear expansivity? Simple limb cancel out. Then remember, units of linear expansivity will be per Celsius. If not, if the temperature measured in kelvins, per Kelvin. Per Kelvin. Okay. So now talking about linear expansivity constant, remember this constant depends on two main factors. Right? I think board is blurred. Right? Can someone respond? Connection is low. Can someone respond? So you want to reply for Sir account, not Suleiman Nawaz. Reply for Sir account. Connection is not good. Put a reply quickly, someone. If you feel it's lagging, put a reply. Right. Now I think it's fine. Mm, voice is in lagging, board is not clear. Okay. Right. We'll wait for 2 3 minutes. Okay. Now quickly write down these things. Referring, quick referring. We are referring quickly. So now we'll wait for 2 3 minutes. Now somehow we should plan to discuss the solid expansion theory points, important points quickly. Somehow we want to plan this. We'll wait for 2 3 minutes. Now I think it will be okay. And tomorrow I'm planning to start unit 3 also from optics. Unit 3 also from optics. Refraction through plane surface. Right. Now is it okay? Hmm. Right now I think it's fine, right? Can someone reply? Still board is blurred? Still board is blurred? Yes. Hmm. Now it's okay. Right, okay. Then we can continue. Now very simple. Now we are talking about linear expansion. There's a lot. There's a rod. Initial length is L1. Temperature increased. Length of the rod has increased. Right. Now I derived an equation for increase in length. If a change in length, delta L means L1 alpha delta theta. I identified alpha as linear expansivity. Now we found units of linear expansivity is per Celsius per Kelvin. Now, talking about this linear expansivity, remember this linear expansivity depends on two main factors. Okay, first point is This linear expansivity depends on the material, right? Depends on the material. And for different materials, this alpha value is different, right? When you consider copper and iron, this constant for copper is a different value. This constant for iron is a different value. For an example, copper, let's say alpha is 5 for an example. Iron, alpha will be 6, right? Linear expansivity depends on two factors. One is the material. Okay, material. Second factor is temperature. Temperature. Remember, now even same material, let's take copper rod. Now, when you take copper rod, remember this alpha linear expansivity changes with the temperature as well. Okay. For an example, when the temperature of the copper rod is 20 degrees Celsius, let's say alpha value is 5. Remember, when the temperature is 30 degrees Celsius, alpha value will be 5.1. But in our syllabus, what we do, we neglect the variation of alpha with temperature. We don't consider alpha variation with the temperature. Now we assume throughout the considering temperature, we consider alpha as constant. But keep in your mind, alpha is a constant, depends on two main factors, material and the temperature. Now, material means different materials, different alpha value, but temperature changes also, alpha changes, but we neglect it, right? In our syllabus, what we do, we consider throughout the temperature, alpha remains constant. Okay. Now, normally this alpha value is a very small value. Okay. So this alpha value is very small. Alpha is very small. How much smaller? Its value is normally 10 to the power minus 5. 2 into 10 to the power minus 5 per Celsius. 2 into 10 to the power minus 6 per Celsius. Think minus 5 means how much? 2 into 10 to the power minus 5 per Celsius means it's very small. 0.0000002. Right? And also, when you compare material, remember, normally we can divide materials into metals and non-metals. Metals and non-metals. Normally, keep in your mind, alpha value is greater in metals, alpha value is very smaller in non-metals. Okay. When you consider iron and wood, iron is a metal, wood is non-metal, right? Linear expansivity of iron is greater than the linear expansivity of wood. So those are the important points you should remember regarding alpha. Okay, alpha. Okay. Now raise your hands. Up to now, everything is very clear. Hands up. This equation delta L equals L alpha delta theta. All these points. If you understood, raise your hands. If everything is very clear, hands up. Now, I think there's a connection issue. Okay. If you understand, raise your hands. Okay. Right. Okay. Then second thing is in linear expansion, what we do, this equation gives the change in length, if not increase in length. If you want to obtain an equation which shows a relationship between final length and initial length. Now see, earlier length is L1. Now length is, I take it as L2. Now length of the rod is, I take it as L2. I think connection issues. Now length is, I take it as L2. So then, how many of you can write on an equation involving final length L2 and initial length L1? Now we know final length, final length we can write down. Final length means L2. That should be equal to how much? Initial length plus increase in length. Am I correct? Final length means we can write down initial length is L1 plus increase in length, that is delta L. Delta L. So then L2 means we know L1. Delta L means how much? Change in length. Delta L means how much? L1 alpha delta theta. Am I correct? Delta L means change in length, that is L1 alpha delta theta. So we can write down Finally, an equation L2 equals L1 1 plus alpha delta theta. L2 equals L1 1 plus alpha delta theta. Okay. So in linear expansion, there are only two equations. Change in length, delta L equals L alpha delta theta. Second one is final length. L2 equals initial length is L1 inside the bracket 1 plus alpha delta theta. So remember these two equations. Remember these two equations. Remember these two equations. Connection is a problem. Okay. Okay. So now in that PDF I shared in the group, what you can do, you can write all these points in that PDF. Okay, in that PDF you can write in all these points. Okay. Mm. Okay. Right. And some special points. Now I told you alpha is very smaller value. The value of alpha is in the range of 10 to the power minus 5. Right. Whenever in equation, when you obtain alpha square terms or alpha cube terms, remember important points. Highlight. Okay. Now, in an equation, when you obtain, if there's a term alpha to the power 2, if not alpha to the power 3, remember, you can approximate to 0. Because we know alpha is very small. Alpha power means alpha to the power 2 means alpha to the power 3 means that is almost equal to 0. So keep in your mind in some equations, you might have to assume whenever there is an alpha square term or alpha cube terms, you have to approximate to 0. Okay, this is an important point. Important point. Okay. Now, then next point in linear expansion is in theory, they talk about fractional change in length. Fractional change in length. Okay. What is this fractional change in length? Right. Now, fractional change in length means remember normally the idea. Fractional change in length. MCQs, they have tested this one. Simply change in length delta L over initial length. Remember, fractional change in length means when we divide change in length by the initial length, that is what we call as fractional change in length. And you can remember delta L means, we know this equation, delta L means L alpha delta theta. So if you write delta L as L alpha delta theta, what will happen? What will happen? You are this L and this L cancel out, then we can write down fractional change in length as alpha into change in temperature. Okay. Remember hereafter, fractional change in length means FCL means remember alpha delta theta. Alpha delta theta, if not delta L over L, that is the equation, but it is equal to alpha delta theta. Alpha delta theta. Okay. Now those are the important points in linear expansion. Linear expansion. Okay. Now based on this idea, based on this knowledge, what we learned, we'll try to do 1-2 past paper MCQs. I shared another PDF. I shared another PDF in the group. Quickly take that PDF. Based on what we learned so far, we'll try to do past paper 1-2 MCQs. Then again, we'll go back to some theory points. We'll go back to some theory points. Take that PDF in the group, PDF shared in the group. Okay. Right. Now we'll do in that PDF 1998 MCQ. 1998 MCQ. Now read the question. If the fractional change in, okay, now that is volume. That is volume. We didn't learn about volume. Mm, okay. What we can do in that one? Okay, right. I think. Mm, okay. We can do question number two. 1992 A level. 1992 A level question number two. Past paper MCQ. PPMCQ. Right. PPMCQ. Past paper. Past paper MCQ. 1992. Question number, I think, two. Now, quickly get the answer. Right. It says that a spiral spring of length, simple L. Number of turns, coil diameter simple D heated from the temperature theta 1 to theta 2. If the linear expansivity of the material of the spiral is alpha, the increase in length of the spiral will be. Okay. Now, theory wise, you learned all the important points. We know delta L equals L alpha delta theta. L2 means L1 1 plus alpha delta theta. Now they are talking about spiral spring of length simple L. Number of turns, coil diameter simple D, heated from temperature theta 1 to theta 2. Linear expansivity of the material alpha. They are asking us to find the increase in length. Right? Now very simple. Now see, in that question, there is the spiral. Am I correct? They have given length of the spiral is simple L. Right? When you measure the length of the spiral, length is how much? Simple L. That means initial length is given as simple capital L. Initial length is capital L. Okay, linear expansivity of the spiral given as alpha. Initial temperature is theta 1. Now temperature increased to theta 2. Then I told you, how can you find the change in temperature? If not, how can you find the increase in temperature? Delta theta means we know delta theta means theta 2 minus theta 1. Okay. Now what they are asking? They are asking the question increase in length. Now, what is the equation we learned to find the increase in length? Delta L equals L alpha delta theta equation. Now we know increase in length means we know that delta L equals L alpha delta theta. See, then length of the spiral is capital L. Linear expansivity of the spiral is alpha. Change in temperature, theta 2 minus theta 1. That is the answer. Theta 2 minus theta 1. See, it's very simple. So therefore 1992 A level answer will be second one. Second one is the answer. L alpha theta 2 minus theta 1. Second one. Okay. Right. Now up to now everything is okay. Hands up. Hands up. How many of you understood so far? Everything is very clear. Hands up. If you understand everything up to now, raise your hands. Okay. Right. Right. Okay. Okay. Now that story is finished. Now the time is we want to look the applications of linear expansion. right? Applications of linear expansion. Now look here. Now, some important points you should remember regarding linear expansion. Okay. The first thing is application one. Application one, some MCQs also there, and also in some essay questions also they have asked the story. Now, just think applications. Now, let's consider now when there is a length, there is a rod, and they have given linear expansivity of this rod is alpha. Initial length is, let's take it as capital L1. Temperature increased by delta theta. Temperature increased by delta theta. Okay. So then what will happen? So then we know that if there is a rod of initial length L1, when temperature increased by delta theta, what we know, this rod undergoes expansion. That means length of the rod increases. That means we know length of the rod increases. Length of the rod increases. Increase in length is, we take it as delta L. Delta L. So delta L equals, we know delta L equals L alpha. L alpha delta theta. If you want to obtain final length, that is L2 final length. If you want to obtain final length, L2 final length is L2. This is L1. Delta L means L1 alpha delta theta. If you want to obtain final length, L2 equals L1 1 plus alpha delta theta. So you already know the story. But remember, just think there is a small gap. Right? Now there's a small gap. Initially, when the temperature is theta 1, very careful understand. Now these are two rods. Just think these are two metal rods. When the temperature is theta 1, you notice there is a gap between these 2 points A and B. There's a gap between these 2 points A and B. And when you measure this gap, this gap is equal to the length of this gap is exactly capital L1. Okay, so this is one story. Now I'm going to explain about another different story, but these two stories behave like same. What I am telling, just think there are two rods, and in between these two rods there's a gap. When the temperature is theta 1, this gap is L1. This gap is L1. Now what happens? Now same thing you are doing. Linear expansivity of these rods are alpha alpha. Alpha alpha. But what are you doing? Temperature increased by delta theta. Temperature increased by delta theta. So then what happens? Now what happens when you notice this gap, you see now this gap is also increasing. Now in a rod, when you increase the temperature, length of the rod increases. That is what we call as expansion. But in here, there was a gap between A and B. When you measure the length of that gap, it is L1. When temperature increase, remember, this gap also expands. This gap is also increasing. This gap length is increasing. Okay. Now this gap length has increased. Now here is your point A. Now here is your point B. Right. And when you measure, remember, when you measure now gap between A and B. Now gap between A and B, let's take it as capital L2. Capital L2. Now in exams, they gave initial gap between A and B, and they give the increase in temperature. Now they are asking you to find the now gap between A and B. Now, in order to find the now gap, remember the way how this gap expands is equivalent to the way how, if this gap is filled with rod with same material, the expansion of that rod. Okay. Now think. Now earlier there was a gap. That gap length is L1. Temperature increase, we notice gap length increases. Now if you want to obtain now length, When you consider the expansion of the gap, that is equivalent to expansion of the gap is equivalent to expansion of a rod. If there is a rod, just think if this gap is filled with a rod of same material, just think if this gap is filled with a rod of same material, right? Then this gap expansion is equivalent to the expansion of the rod between them. In case if this gap is filled with the same material, the expansion of this material is equivalent to the expansion of the gap. Do you understand? Do you understand? So therefore, in this case also, what you can do, you in order to find the now gap, you can use same equation. Now gap is L2, previous gap is L1, 1 plus linear expansivity of the material, right? Who is now gap is in between. Who is the material? Alpha, delta theta. Okay. Now, whenever there is a gap, sometimes in exams they can give the first point is now they give a gap. They give a gap and they ask you to find the final gap between them. So remember, in that case, what you should do is you want to assume that gap is filled with the same material. If the gap is filled with the same material, the how that expansion of that material happens. Just think this gap is filled with the same material. That material is expanded to this level, right? Apply the linear expansion equation for this material. Then you can write down something like this. Then you can write something like this. Okay. Okay. So that is one story. That is one story. Right. Now then in MCQs, next you get, right. Now there are light poles, right? Now there are light poles. Just think a wire is laid in between these two light poles. So this is your road. Okay. This is your road. The ground. These are light poles. Light poles. Okay, light poles. And think a wire is laid like this. Now, the day where you lay on the day where you laying the wire has a temperature theta 1, right? So when you are laying the wire, temperature of the surrounding is theta 1. 30 degrees Celsius, for an example. Now, what would happen? What would happen when the temperature of the surrounding increases? When the temperature of the atmosphere increases, my question is, what would happen for the wire? When temperature increases, what would happen for the wire? When delta theta increases, what will happen? This length wire undergoes expansion. That means length of the wire increases. Then you see between these two poles. So the appearance of your wire would be like this. Am I correct? Length of the wire is increased. Then this is how your wire looks like. Right? Initial length, just take it as this length is L1. This length is L2. Then which one is larger? When temperature increase means we know L2 is larger than L1. Am I correct? Now what will happen? What will happen when temperature of the atmosphere decreases? When temperature of the atmosphere decreases, what would happen for the wire? Till now, I explained expansion means when temperature rises, length increases. Now, what would happen when temperature decreases? What would happen for the length decreases? That means length undergoes compression. Length undergoes compression. So when temperature increases, length increases. Temperature decreases, length decreases. Temperature decreases, remember, length decreases. That means when temperature decreases, now length of the wire decreased. Then how the wire looks like? How the wire looks like? Your wire looks like something like this, right? The wire looks like something like this. Now, if I say initial length is L1, final length is L2, final length is L2, then which one is larger? L1 is larger, L2 is larger. Temperature decrease means length is decreased. So then L2 is smaller, L2 is smaller, L1 is larger. In that case, L2 is smaller than L1. Now, these are some important MCQ points, right? Now, Bimetric strip story. Okay, now this is tested in many times in exams also. Now what is basically bimetric strip? Look here, bimetric strip story. Next one. Now bimetric strip means, remember, when you take two different materials of equal length and when you revert them together, right, that is what we call as a bimetric strip. Okay, just consider now you are taking copper and aluminum for an example at a certain temperature, let's say theta temperature. If for theta 1 temperature, you take copper and aluminum. Consider this black one is copper and this red color one is aluminum. Okay, red color one is aluminum. What you do, you keep this copper and aluminum on top of each other. They both of them have same equal length, and you revert. If not, you weld them together. If not, you revert them together. Okay, you weld them together. If not, you revert them together. Then combination, this combination we call as bimetric strip, right? This combination we call as bimetric strip. Bimetallic strip, a bimetric strip. Today connection is very weak, right? Okay, right. Okay. Again, connection problem. Now, somehow, if we can finish all these important MCQ points, then I think we can do all the past paper questions. That's the plan, but time is 10:12. Okay. Because today I'm at Kurunakala. That's why. Hmm. Okay, now we'll do something like this. Because now connection is not good today. It's a problem because even let's say now if you are facing this connection issue, so then at least you can watch the recording later if there is any issues, right? I think the issue is with me. Now connection issue is not with you, but this issue is with me and my location. So therefore this recording also has same issues. Even you watch the recording also, same issue is there. So now what shall we now? We'll do something like this. Now I want to finish this solid expansion, area expansion and volume expansion, small parts. But lean expansion, there are many applications. I won't describe every application quickly, right? Then we can do past paper discussion. But the problem is this connection issues is a big problem. So what we can do, we'll schedule today's class. Uh, we'll schedule today's class on Saturday. Saturday, I plan to keep a paper, right? I plan to give a paper, but we'll schedule now. Okay. Mm, now I think it's again okay. Okay. Anyways, we'll schedule it on Saturday. I will tell you. We'll do like that. Okay. Now I will brief it. Okay. Now, linear expansion, we are talking about linear expansion. Then, you know the two equations. and we are talking about some of applications. I think I discussed some applications, but still I want to teach you about biometric strip, the way how it bends, and then I want to teach you about what happened for the time period of simple pendulum with the change in temperature. Then we are learning about what will happen for the scales, especially these measuring instruments like meter, ruler, vernier, meter. What would happen when temperature changes? What would happen for the reading on the scale? And some related application points I want to teach you. Right, then we can finish this linear expansion point wise quick revision. We can complete it, right? But today I plan to cover, but I think there are some issues today. Okay, okay, we'll go with a small poll. Shall we do Saturday? Is it okay, hands up? Shall we continue on Saturday? Is it okay? Because beta, I think we can continue on Saturday, right? Better. Okay. So then we'll do that on Saturday. And okay. Now just put a small reply now. This way is okay. I think now we should do some questions. I wanted to revise everything quickly and I want to do the questions. Right. If you're okay, just put a reply the way how the today class is going. Put a small reply. And okay, we'll work. We'll work today, I think, because I'm in Kurunakal, not in Colombo. Okay, we'll work. Okay. So we'll stop the class for today. See you. Bye.